Okay, so today I'm going to do a tutorial on the practice statics exam. So apparently this exam is on Wednesday for you guys, and some of you have been freaking out about how to do these problems, so I'm going to try to give you a, strategy for attempting each of them. And what you're going to see on the exam is something very similar to this. This is last year's exam. It's 3 questions and 55 minutes, so you're going to have to work fast and you're going to have to work efficiently. Okay, so this is an example of a problem where they want you to resolve a system of forces. In this system we have two, F1 over here and F2 over here, into some condition. Typically, they have them all equal 0, but in this case we're going to have 500 newtons along the x-axis. That isn't that much of a difference from usual. It doesn't actually change the problem that much. The core of this problem is trying to figure out what to do with these angles. These are called coordinate angles, and they are from the force to each coordinate axis. And this is when you'll be dealing with angles that are occasionally greater than 90 degrees, which you don't really work with for the rest of the course. So this is a first exam question that you're probably never going to see again. Okay, so how are you going to deal with this? The good thing is that in giving you these parts, they pretty much tell you what you're going to be doing. So the general strategy is to find a way to represent each of these force vectors along each axis. And generally the way you do that is using I, J, and K components. I'm going to use the angular bracket notation that you see in multivariable calculus. So that's just if you have a I plus B J hat plus C K hat, that's the same as this. So on the exam, give something in this form, and it's not that difficult to go between the two. Okay, so let's start with F1. So the difficulty that a lot of people have with this sort of problem is, how do you separate the components of this force vector into the different axes? So let's start with the easy one. If you can't see, this angle is 18 degrees. So if we're looking at the component along the z-axis, that's just straight vertically like this. For F1 going along here, we could easily tell that it's going to be this component. Okay, and it's kind of hard to see this in 3 dimensions, but this is a right triangle. It doesn't look right because we're looking at it in 3D, but there's actually a right angle here. That means that this is the hypotenuse. And to get the z component, what we need to do is 180 sine 18 degrees. Oh, sorry, that wasn't 18 degrees, it's actually a 15. I'll draw that out here. 15 degrees, sorry for that earlier. Okay, so sine 15 degrees because we're going to the opposite side of the angle, okay? The more important part that people usually mess up is which sign is this going to have? Is it going to be positive or negative? For that, you look at where the coordinate axis is labeled. So here we have z facing upwards, and we have the vector going downwards. So this is going to be negative, because if we just look at this component, it goes in the opposite direction of the labeled axis, okay? So I guess I'll leave some space here. This will be the x component, this will be the y component, we just found the z component. It's going to be this. Okay, and I'm kind of sneaking the magnitude of the entire force vector into here. What you can do is you could pull it out, because you're actually going to distribute this magnitude over each of the components of your unit vector. How do I know it's a unit vector? Well, we're using trigonometric functions. So if we end up squaring all those, they will come to 1. So getting the x and y components of F1 is a little trickier, because first you have to project F1 into the xy plane. So if the sine gave us this component, the cosine will give us this. So to take this f1 into the xy plane, we need to do 180 cosine 15 degrees. But that only gets us this line. We then have to break this into components along the x-axis and the y-axis. Okay, so then we're going to use this angle over here. So if we're trying to get the y component, we're going to use the cosine. Why the cosine? Well, if you look at this, this is another right triangle. Again, it doesn't look like a right triangle, but it is a right triangle. And the hypotenuse is going to be, well, it's going to be this. So if this is our hypotenuse, and again it looks skewed, so it's a bit strange, if we take the cosine, we're going to get the component along the y-axis. Okay, and the last thing we need to note is this quantity going to be positive or is it going to be negative? Well, if we took this and we just took the component along here, it points along the same direction as the coordinate axis. So in this case, it's going to be positive. So I'll put that in here. A lot of people are scared by having two trig functions multiplied by each other. Don't be, it's not really that big of a deal. Okay, so if you might have guessed, the x component is just going to be the sine of 60. Why the sine of 60? Well, we're taking the opposite side of the right triangle, which is here, and that's parallel to the x-axis. Again, is it going to be positive or negative? Well, this here, pointing along the same direction as f1, is going to be like this, which is again parallel in the same direction as the coordinate axis. So it is also going to be positive. So 180 cos 15 degrees, again, bringing this up to here, and then the additional sine 60 degrees takes this along here or here. Alright, so that's the tricky part out of the way. The other force we have to deal with is F2. Okay, in this case, we don't know the magnitude of F2, so I'm going to pull it outside of the angular brackets. Again, that means we're going to technically distribute it in each of these three components. Much like we could have taken the 180 outside of the angular brackets and distributed it into each of these components. Okay. So the coordinate angle, which are given in Greek, simply tells you the cosine that you have to take to get it onto that axis. Nothing more, nothing less. You don't have to worry about anything else. So here, it's because it makes a right triangle with each of these axes. In the case, well, actually, probably a bit misspoken on that because B is going to be, or beta is going to be greater than 90 degrees. But it works out probably from the law of cosines. Anyway, all you have to do is take the cosine to each coordinate axis. So the angle between the x-axis and F2 is alpha. So all we need is cosine alpha. Again, the entire x component would be the magnitude of F2 times cosine alpha. But this is just a unit vector here. To go along the y-axis, we're going to need cosine of beta, and I guess I'll put the 2's here because problem had them already. And for the component along the z-axis, we're going to use cosine gamma. Okay, so what tripped some people up and what tripped me on the exam when I originally took it is how do you account for the direction of each of these components? Well, for x, that's easy. It's kind of pointed in the x direction, so this goes along this axis in the direction of this axis. That's positive, that's fine. Z is also okay because, well, it goes up and Z goes up, and you take the component along here. It goes in the same direction of the coordinate axis. But what about beta? Okay, well, this is pointed away from the y-axis. Yeah. So ordinarily, if we were doing it before, we would have put the negative sign on this term. But here's the tricky part about working with coordinate angles. Beta is greater than 90 degrees. So what that means is if you have a cosine that's between 90 degrees to 180 degrees, we're talking quadrant 2 over here, that's going to be a negative quantity. What that means is when you take the cosine of this angle, a negative sign will come out, which means that this has already been accounted for. The angle accounts for the sine in this case. So if we added another negative sign, we would be double counting the negative signs, and we'd have this pointing in the wrong direction. So just remember, when you're dealing with coordinate angles, the sine is already included in the coordinate angle. Okay, so that aside, the last thing we have to do is resolve it into a resultant force. So what that simply is you add up the forces for this resultant force, and they tell you what it's going to be. 500 newtons along the x-axis, which means that it's 0 along the y-axis and 0 along the z-axis. The only other thing you have to do at this point is set up equations. With this, you could again resolve these into I, j, and k components to make the Cartesian vectors. What we want to do now is determine alpha, beta, and gamma. Okay. What you should realize at this point is that we sort of have a little bit of a problem, but I'll postpone that discussion for another 30 seconds or so. Okay, so if this wasn't already clear, we're going to add the x component of this and the x component of this. So you get 180 cosine 15 degrees, sine 60 degrees, plus, remember, don't forget this magnitude out here, we have to distribute that in. I'll draw arrows this time to make that clear. And the magnitude of f2, cosine alpha 2, plus, well, no, I won't confuse you guys, equals, remember, f1 plus f2 equals the resultant force, so these two components here of f1 and f2 must equal 500. Okay, and so this is our x equation. For the y, we do the exact same thing. And again, technically this term is going to become negative, but we don't really have to worry about that. This is going to be 0. And lastly, you have this, which is also equal to 0. Okay, so the problem is that how many unknowns do we have? We don't know cosine alpha, we don't know cosine beta, we don't know cosine gamma. We also don't know the magnitude of f2. We have 3 equations and 4 unknowns, which means we cannot yet solve the system. We need another equation. Okay, and what is that equation going to be? Well, it turns out this is something you gotta know. It comes from an extension of the Pythagorean theorem into 3 dimensions. It is that the magnitude of f2 is going to be the square root of the x component squared, the y component squared, and the z component squared. This is when it gets a little bit messy, because we're looking at f2. So again, distribute this in. Cosine alpha squared, f2, the magnitude again, cosine beta 2 squared plus the magnitude of cosine gamma 2 squared. Okay, and what's interesting is that you could actually distribute this magnitude of f2 squared, square root it and pull it out. What you'll get is magnitude of f2 over here. So what we're actually looking at is this equation. Alpha 2 squared, well, typically it's written the squared over the cosine. Beta 2, cos squared, gamma 2. Okay, so now we have 4 equations and 4 unknowns. So at this point during the test, you could solve this equation. The way I'd recommend doing it is isolate cosine alpha, cosine beta, cosine gamma, solve for these, sub them in, and what that will find you is f2, and then all you need to do is sub f2 back into each of these, and you'll find, by using inverse cosine, each of the angles. If you want to try the problem yourself, the values are up here, so that's what you're supposed to get. Okay, when you're actually taking the test, once you get to this point, I recommend just going on to the second problem and then going on to the third problem. You only have 55 minutes, so remember, you need to work as quickly and efficiently as possible, so save the algebra to the end. Because if you don't get to a problem, you're not going to get any partial credit. You can't go back in afterwards and get anyone to give you partial credit. So just get this set up as fast as possible. Okay, so let's look at the second problem from 2013. Okay, so again, kind of the same things going on. Now, the first thing they'll ask you to do is draw an FBD, but pretty much what they give you already is an FBD. So if you redraw what they give you, you will pretty much get 10 points. The only thing that might have been a bit tricky here is if you see these two, I guess, things over here. These were struts originally. What struts do is they push. So the force will go from the strut to the point you're considering, which happens to be B here. So these two are struts and the forces go out. This is like a line, so like a string or a rope that goes along. What that does is it's a tension, so it pulls from the point you're considering back to the object. Same thing happening with the bag that's located on this line. It's pulling from the point while these struts push. So be able to recognize when something is either in tension, so it's pulling, or if you're dealing with something that pushes outward like a strut. Okay, so basically this question is asking you to write a force vector for each of these 4 forces, and then solve systems of equations to find out what the magnitude of each force is. So again, this pretty much the same exact thing is going to happen in every problem. So the way we're going to start it is we're going to look for position vectors. So just lines that describe each of these forces. And again, it's going to be a bit tricky because you have to get the positive and negative signs correct. If you don't do that, you're going to have a bad time, and you really want to double or triple check them before doing the problem. So let's start with a position vector from B to D, because again, the force is going in tension from B to D because the rope is pulling it. Okay, so first, how much do we move in the X direction, or along this X axis here? Okay, well, our point B is located here, which is on the y-axis, and it goes to a point along the y-axis, D. So it does not move anywhere along the x-axis. So that's 0. Okay, what about its movement along y? Well, it goes against the labeled coordinate, so it's going in a negative direction. First it goes in -4, and then it goes in -5.6. And again, we're going from B to D. That's why it's negative along here. Okay. And lastly, the Z component. Well, we're going from B to D downwards. So that distance is given by this. So we're going -4. Okay. The next force we can do is from A to B. Because again, this is a strut, it's pushing like this. Okay, and along the x-axis, we're going 2, because again, this is located on the y-axis, which is this line. So we're going 2, but are we going positive or negative? Well, again, x is labeled this way, so we're pointing in the opposite direction as x. So we're going negative 2. Okay, are we going anywhere along the y-axis? Well, yes, we are. So this is the y-axis, this is how the coordinates labeled, and we're going from here to here. So we're going a distance 4 meters, positive. And lastly, are we going anywhere along the z-axis? Well, from A to B, we're going up, so we're going 4 up. Okay, same thing with CB. This is pretty much symmetric except for in the x direction. We're going towards this point, which is along the y-axis, so we're going like this, which is a distance 2 meters. We're still going this way, and we're still going this way. So we have 4 and 4. Lastly, we have the position vector of, I guess, the weight, which is just directly down. We'll worry about that later, I guess. It's not really instructive to consider that as a position vector, because a lot of people get confused. In any case, once you've found position vectors, what you want to do is you want to make a unit vector, because all the forces is simply a magnitude projected along a line. In other words, you're just going to take the magnitude of a force, multiply it by a unit vector for a line. So how do we transform these position vectors, which the magnitude isn't 1, that's the requirement of a unit vector. If you take the square root of the squares of each of these, you're not going to get 1. What we need to do is we need to find the magnitude of each of these. And the magnitude is simply going to be just that, the square root of the components. So in this case, 0 squared, negative 9.6 squared, I just added those up, and negative 4 squared. Here, negative 2 squared, 4 squared, and 4 squared. Lastly here we have 2 squared, 4 squared, and 4 squared. So if we wanted to get unit vectors, all we need to do, say we get unit vector of along BD, we take each of these components and we divide by the magnitude that we just found, which we'll just represent as this, because that's kind of a nasty calculation to do. And at least if you're describing what you're doing with the vectors, whatever TA is grading your exam could easily tell what you're doing, rather than just, alright, negative 5 point whatever. That doesn't really mean anything. Okay. So once you have the unit vectors, all you need for the force is to take the magnitude of that force times the unit vector. So if we wanted the forces, FBD, FAB, FCB, all we need to do is multiply the force by the unit vector. And again, we know this, these are all known, but this is not known, this is not known, and this is not known. These are what we're solving for. So we have 3 unknowns. The last thing we have to do is set up static equations. It's a weird looking cue. So the sum of the forces in the x direction is going to be 0. So that's going to be 0 times the force along BD, -2 over the position vector times the force along AB. Again, I'm just reading off the x components divided by the magnitudes. PCB. This is going to be equal to 0. So all I'm going to do is do that twice more for the other two. And this is probably going to take a while to write. Okay, and I guess the important part, or at least why I write it this way, is because for the first 2 common hour exams, you will have the opportunity to use a graphing calculator, or at least that's how it was when I took the course. There was actually an announcement from Savat, who's one of the TAs for the course, telling us that we could do that. Let's see, I'm trying to do this at the same time. Things get a little complicated. There's a lot of 4s. AB and 4 over PCB, FCB equals 0. So this looks complicated, but if you can put this into a matrix, I don't know how long that was cut off, sorry for that. All you have to do is make something of the form with these as your coefficients. So you put each of these numbers that are not circled into here, RAF that, and you'd have an answer. That scares you, don't worry about it. For those of you that do care about it, I'll go over after I do the third problem. Okay, so the last thing that you'll be tested on is something regarding moments, or how to deal with moments. And a lot of people, for some reason, are not so good at dealing with moments. So, we'll give that a shot. Looking if I see another color. Okay, purple. So in this question, we're looking for the weight of the components inside of the wheelbarrow. And we were told that the resultant moment about A is going to be 0. It should say about A in the question. That's pretty important. And the reason you use moments is because if we simply look at the force of gravity going down here and the force that we're told is being applied on the wheelbarrow, you could tell that there is no horizontal force over here, so this system is not balanced statically in the horizontal direction. In other words, we have a leftward force over here and no rightward force. So static equations aren't going to be able to tell you the weight, because you'd be assuming that it's balanced in the y direction. It's not necessarily balanced in the y direction. We are told that the moment is 0 though, so we can use that. Okay, so how do you do problems with moments? Well, the easiest way to do that is simply, you know that a moment is a torque, and a torque has a radius arm and a force. So all you need to do is find vectors that represent the moment arm and vectors that represent the forces, and then take the cross product of them. Okay, and again, we're evaluating the moment about A, so we're going to need radius vectors from A. So what do I mean by radius vectors? Okay, or moment arms as they're often called. So a radius vector is simply a position vector that you do not need to unitize. You don't need to unitize it because you're not projecting a force along there, you're crossing a force along it. So I guess I'll try to make this a bit more obvious. Our moment arm is going to go from A to G. So along here. It is going to have an x component and a y component. The x component here is pretty obvious. It's 0.3, and the y component here is 0.5. That's all you have to do. The force of gravity is going to be nothing in the x direction, and it's going to be going down, so negative, and we're trying to figure out the mass, so it's going to have mg. That's it. The other moment arm you have to worry about is one going from A to B. So we have this happening. In the x direction we're going to go 0.3 over, then 1.2